Robotics has rapidly moved from repetitive mechanical tasks to highly complex, fully autonomous operations, navigating unpredictable environments. For years, the Robot Operating System, or ROS, provided the open-source infrastructure to make that possible. Today, modern hardware demands are overwhelming that original design. Pushing into fields like autonomous vehicles and aerospace requires real-time processing and strict security protocols, capabilities the original system was never engineered to handle. This creates a direct dilemma for engineering teams. You can choose the mature, massive plug-and-play ecosystem of ROS1 or take on the significant technical hurdle of migrating to ROS2. Royal Research highlights that shifting to ROS2 requires a total architectural overhaul of the system's foundation, rather than a standard software update. We need to look past the hype to objectively weigh how this choice impacts your system's performance, its core security, and your team's development timelines. Developers have to decide whether to trade immediate, frictionless prototyping today for long-term scalability and robust deployment tomorrow. Choosing the wrong operating architecture delays product launches and permanently dictates whether a robotic system can safely survive in a real-world commercial environment. This flowchart shows the baseline architecture of ROS1. It relies entirely on a centralized master node that routes all connections and data to the machine's various peripheral nodes. The primary benefit of this master node is that it handles all networking logic for you, drastically simplifying initial setup and basic development. But this centralized hub creates a massive trade-off. It acts as a severe single point of failure for the entire machine. If that master node crashes during an operation, every node loses contact, the system goes blind, and the robot stops functioning entirely. ROS2 solves this by removing the master node entirely, replacing it with a decentralized architecture built on the Data Distribution Service, or DDS. Under DDS, nodes automatically communicate on a peer-to-peer basis, meaning no single failure can take down the network. The trade-off is a much steeper initial learning curve. Developers now have to manually configure these distributed network rules themselves. This also changes communication latency. ROS1 uses a custom transport layer that works perfectly fine for basic low-stakes data transfer in a controlled lab. But that legacy layer restricts real-time capabilities because its parameters are rigid. ROS2 utilizes quality of service policies via DDS, prioritizing critical data streams like immediate stop commands from LiDAR sensors over background chatter. Implementing these QoS policies increases network configuration complexity, but it guarantees that priority data arrives first. Without a decentralized architecture and prioritized data routing, systems cannot guarantee the real-time latency required to prevent fatal errors in high-stakes environments. Beyond external network communication, we have to look at the internal processing limitations of legacy robotics. ROS1 operates on a single-threaded executor model, which takes a predictable, linear approach to executing code, one step at a time. This chart illustrates the problem. A single thread places a hard cap on processing speed because it fails to utilize modern multi-core processors. ROS2 removes this bottleneck by introducing a multi-threaded executor model natively. By distributing tasks across multiple cores simultaneously, it increases processing speed and computational efficiency for heavy workloads like real-time mapping. The trade-off is that developers must now write complex, thread-safe code to prevent memory conflicts, which raises the bar for software engineering competence. Then there is the strict security imperative required for modern robotics. ROS1 allows for fast prototyping because it has zero built-in security overhead. Any device on the network can read or write commands. If you deploy ROS1 in the field, your commercial networks are left vulnerable to external interception or malicious takeover. ROS2 bakes in DDS security features, enforcing mandatory node authentication, robust data encryption, and strict access controls. Deploying unencrypted legacy software in commercial fields leaves physical machines vulnerable. ROS2's added security configuration is essential for field-ready commercial operations. We need to address a central challenge regarding this transition. ROS2 is not directly backward compatible with ROS1. Upgrading means accepting a heavy upfront engineering cost. You either have to carefully migrate your specific packages or rebuild your legacy system entirely. This decision tree asks the core question developers must answer. What is your actual deployment environment? It branches into two paths: stable legacy or commercial real-time. Let's map the first scenario. You are maintaining existing, stable agricultural robots or doing basic manufacturing R&D in a closed lab. In these specific, highly controlled environments, millisecond real-time latency and heavy network encryption are largely non-issues. The outcome here is simple. You save massive migration costs by sticking with what already works for your hardware. The trade-off is that you are building on a legacy platform with a shrinking future horizon, though community software bridges exist as a temporary stopgap to communicate with newer systems. Now let's map the second scenario: teams building autonomous vehicles, aerospace technology, or distributed multi-robot systems. These industries categorically fail without real-time performance guarantees, multi-threaded processing, and strict data encryption. If you are on this path, you must accept the steep upfront cost of migrating your codebase into a newer, rapidly evolving ecosystem. The long-term return on that significant investment is having the enterprise-grade features required for commercial viability at scale. If a robotic system's failure has real-world physical or financial consequences, the decentralized, secure architecture of ROS 2 represents the baseline standard for the future.